Ok, ci siamo. Welcome everybody to today's webinar for Genome webinar. Today we have Davide Cozzi. He's currently obtained his PhD in computer science in University of Milano-Bicocca, and he's now a postdoc over there. During the PhD and continuing forward, he has become an expert in the Positional Burrows-Wheeler Transform, which is a very key and important data structure that is being used, and it's probably will continue to be used in many methods and in many interesting topics in bioinformatics, and I'm sure he will tell us more about it. So thank you, Davide, for accepting this invitation, and the stage is all yours.
Thank you, Simona. Good morning, everyone. Today, as Simona introduced, I will talk about the positional Burrows-Wheeler Transform, which is a key data structure used since from 2014 in more or less each field that requires, for example, genotyping, haplotype phasing, or solving other biological issues like that. First of all, what we will see today, we will see a quick overview on the context, a very brief presentation on the core data structures of the PBWT, some extension proposed over the last years, not by me, but by other researchers. And finally, I will present you the mu-PBWT, which is my main work, which is a length encoded variant of the PBWT able to compute matches with an external query. Probably you know better than me how we can get a binary matrix to represent haplotypes, but just take this example. We have a bunch of chromosomes with some SNPs, and these SNPs can directly identify the haplotype of a sample, but it's not quite efficient to store directly the letters. So for example, in the first column, we can store A and G, but they are not efficient to store in memory, but also on the disk. So we can use binary matrices. We can replace the A with a 0, the G with a 1. And if our sample is biallelic, we can get a binary matrix. So from a computational point of view, we consider a binary matrix where each row represents an haplotype, each column represents a biallelic site, and we are interested in query an external haplotype. So we have a binary string with the same number of columns, so the same number of positions at any other sequence in our panel, and we want to compute some kind of match. For example, in this picture, we have in blue the set maximal exact matches shared between a portion substring of our query and some substrings in the reference panel. So I'm a computer scientist, so I want to speak about something more theoretical than biological. So what we are considering, we have a set of double-long sequences xi, which form a panel of haplotypes, so a set X of this kind of sequences, and the external haplotype is a double-long pattern Z. What is a match? A match is a triple, A, B, E, such that we have a match from B to E shared by the query and each haplotype in the set A. And this match can be defined as set maximal if it cannot be extended neither to the left nor to the right without introducing a mismatch. And there is no other sequence in the reference panel that share a longer matches that cover the same exact positions. So let's talk about the main topic of this presentation, the PBWT. But to understand the PBWT, we need first to recall some very basic knowledge about the classical Burrows-Wheeler transform, which is probably the most important data structure in text indexing since the 1994, when it was created. And it's based on the rotation of, you take a string, you take all the string rotations, and you sort them in order. And you take this last column as the PWT. Let's keep this very boring text introduction. Let's focus on example. We have our text, so Mississippi. We sort in this matrix all the rotations. We just take the last column as the PWT, and we just take the order of these rotations as the suffix array. Using this data structure, we can compute, probably as you know, matches in linear time, and we can compute a lot of fun stuff. But all this core concept can be generalized from the string to a matrix. In fact, in 2014, Richard Durbin proposed the Positional Burrows-Wheeler Transform, which is directly based on every idea of the Burrows-Wheeler Transform and can be used to index and query binary matrices, so haplotype panels with only biallelic site. The key point is that we have 2 dimensions, so we need to compute a transform for each column. And to compute this transform, we need to use a sorting as in the PWT, but in this case, the sorting is the collective graphical order up to the previous column with respect to the one we are considering. Again, let's focus on an example because it's much, much more easier. We want to compute the PBWT of column 5. So what we do, we sort each prefix up to column 4 in collexical graphical order, so from the right to the left. So as you can see, we have 0, 0, 0, 1, 0, it's just the first. For the second row, we have exactly the same values. Then we have 0, 0, 1, 1, which are the prefix of some sequences in our reference panel. In detail, the first row is the prefix of the row 14 in the input panel, the second one, the row 15, and so on and so forth. This ordering as the suffix array in the PWT is stored in a specific array called prefix array. So we have one prefix array for each column. Then, like the LCP in the classical BWT, we have something similar to store how much are different 2 consecutive rows in this ordering. So again, focus on, for example, the second line. We have that it's completely identical to the previous row in this ordering. So we just store that the match from these 2 consecutive rows start in column 0. Then consider the next one. We have that the matching suffix of this prefix starts in column 1. So we store column 1. This divergence array, again, we have one divergence array for each column, is fundamental to compute matches when we are exploring the PBWT. But if we want to make a comparison again to the PBWT, what is the PBWT? Is the concatenation of all the PBWT columns. So we have sorted up to column 4 to compute stuff for column 5. And the next bit, using the same ordering, build the PBWT column, which presents a very peculiar behavior, just like the classical BWT. Do you know that the classical BWT was firstly developed to compress text due to the fact that it can be very easily run-length encoded? The PWT works exactly in the same way. Just imagine that you have 2 haplotypes that are very similar. If they are very similar up to column 5, probably they will share the same bit in column 6. So if we are building the PBWT for column 6, mostly you will have the same bit in 2 consecutive positions. Hence, this column, if the data are, it's not a random matrix, but a matrix produced by an haplotype reference panel will be very easily run-length encoded. What is a run is just a substring, a maximal substring of the same character. For example, here we have a run of 2 zeros, then unfortunately just 1 0 and 1 1 1 0, which are 2 different runs. Then we have a run of 4 ones, and finally a very big one of 0, a very big run of zeros. What we did in the last few years is just to not store the entire PBWT column, but just these runs. But we will see how we have done this in a very few slides. But first, just a brief overview of the literature. Thanks to the original PBWT of Richard Durbin, prefix arrays, divergence arrays, and the PBWT columns, HPBWT columns, can be computed in quadratic time, so just in linear time if you consider size of the matrix. And in the same paper, Richard Durbin proposed also some kind of problems that can be solved. So for example, matches longer than a certain L value, or all the set maximal matches just considering the rows in the reference panel, or as I show you in the example a few slides above, how to compute set maximal matches using an external query. This is a very nice example of how many set maximal matches can you have inside a panel, while as we consider an external haplotype, this number of matches reduce a lot. This is quite interesting because if we look at the time complexities, we discover that the set maximal exact matches inside the panel can be computed in a time linear to the size of the matrix, while we are computing the prefix and divergence array. On the other hand, if we just want to compute the matches with an external query, we need first to preprocess the entire panel in quadratic time / linear time size of the matrix. But each query can be computed in linear time. Linear, in this case, on the number, on the size of the query. But, so you can say, okay, this matching algorithm is very fast. Even if we have a lot of matches, we mostly don't care because it's pretty much linear in the size of the query. But the key point is the space bounds. Because to compute all the matches inside the panel, we just take a column, we compute the stuff for this column, we save somewhere some pointer to the matches, and we drop the column. So it takes just the number of rows, a big over the number of rows as a space. But if we want to compute matches using an external query, we need to store the index for the whole matrix and keep it in memory. And this takes a space that is linear to the size of the matrix, and in a more practical way, 13 the size of the matrix bytes, which is massive. If we consider that, for example, for a very small panel from the 1000 Genome Project, we have 5,000 rows and a couple of millions of columns, it can take up to 500 gigabytes of memory, which is not so good. Some further consideration. The first one, I already said this, that you can compute each kind of internal matches at the same time you compute the prefix and divergence arrays. And another interesting thing is that Richard Durbin didn't discuss this algorithm in his paper, but you can also solve the set maximal set matches with an external query by just including this query in the reference panel, compute the internal matches, and just report the ones that includes this query. Moreover, in the last few years, we also extended the notion of set maximal exact matches to consider at least k rows in the panel. So with this kind of problem, we want to include a sort of coverage notion in our matching algorithms. As in this example, we are computing all the 3 set maximal set matches. And as you can see, you expect to have more matches than in the classical case. Moreover, we also explored some other kind of covering problems, such as the MPSC, so the minimal positional substring cover. So without entering in the theoretical details, find a way to cover a certain query using the minimum number of non-overlapping substrings. We will see a use case for this kind of theoretical problem very soon. Here you have an example. So to cover the pattern, we can just split the SMEM because the MPSC is strictly related to the set maximal set matches in a way that we can cover the entire pattern with the minimum number of substrings without any overlap. Finally, we also extended this notion of MPSC because they are also present in literature. For example, to consider the MPSC that starts as early as possible or as late as possible, or again, to find a 2-level coveraging. So we have the MPSC that cover the query, but also we impose a minimum number of rows for each substring. And this slide concludes our very brief review of the literature. This is a non-comprehensive list of additional extensions of the PWT that we have in literature. We have, for example, the multi-allelic PBWT, which generalized all the stuff that we already said to an arbitrary alphabet. We have the dynamic PBWT, which replaces the arrays with the linked list to provide the possibility to add or remove haplotypes very, very efficiently. Or we also have some additional data structure, for example, the PBWT with the linked equal alternative position, which is a very cost-expensive data structure used to perform L-long matches very, very fast. Then we have works like the scalable PWT, which try to reduce the space requirements of the PWT if we want to consider an external haplotype. And finally, we have the parallel PWT, which is an attempt to apply parallelism to a very linear algorithm like the ones of the PWT to construct prefix and divergence arrays. This one is, another PBWT extension, which is developed in our lab, so I want to have it in a private slide. And is the wild PBWT, which try to compute matches inside a panel with wildcards, where wildcards are values that can assume each kind of possible value of our matrix. For example, this wildcard can be 1, 2, or 0. And we want to compute maximal matches in this scenario. So let's talk about the mu-PBWT, which is my main work. I started working on this during my master thesis when I explored some run length encoding technique. The problem I want to solve is the set maximal set matches against an external query. So the problem is that the original implementation takes 13 the size of the matrix bytes. We want to perform it in sublinear space. So after a sort of exploration of multiple data structures, strongly inspired by all the result of the R index that we already have for the classical PWT, we defined in 2023 the mu-PBWT, which is de facto an R indexing of the PBWT. We need to introduce a new variable. So we don't scale on the size of the matrix, but we scale on the number of the runs, which is sublinear with respect to the size of the matrix. And I want to stress the fact that this kind of results, as we will see in the experimental section, strongly reduce the space requirements. And in a world where we have large population scale biobanks, such as the UK Biobanks, we need something that compress all this massive data, but without having a strong trade-off on query time. We also generalized the use of the mu-PBWT to solve other kind of problems, such as the case at maximal exact matches or the MPSC problem. And we also tried to use it to solve a more biological problem, such as the genotype resolving problem. To understand how it works, the mu-PBWT, we first need to present another matching theoretical results, which is called the matching statistics array. The matching statistics array is an array of pairs, row n, with the same size of any sequence in our reference panel. And for each position, we store a left maximal matches shared by our query with the row specified in the row field of this pair, which has length equal as the length value specified in this pair. Why we need the matching statistics? Because they encode left maximal matches, and if two length value, if we consider two consecutive length values, and the first one is greater or equal the next one, we can also report that this match is right maximal. So if it's both left maximal and right maximal, we have a set maximal exact match. Again, this matching algorithm, matching approach is directly inherited from the results on the classical BWT from the R index, MONI, FONI area, which is quite interesting if you want to go deep on this. So let's see how we can use the mu-PBWT to compute match. I will show this example before talking about what is the mu-PBWT, because I think that is easier to understand with an example. The idea is that we need something, the mu-PBWT, which is a compression of the original PBWT, but which is able to compute 3 operations, more or less. So we start from a certain position in the first column of the PBWT. Imagine that you have the whole PBWT. We have our query Z, we have a match, so we store that in row 19 for position 0. We have a match of length 1. Then we need something in the mu-PBWT that move us from column 0 to column 1 on row 19, which I recall you is sorted, so it's not the last row, but is somewhere else. In this case, if we can access the prefix array of column 1, we will see that in position 14, we have the value 19. So if we want to follow row 19, we need to go to row 14 in column 1. And we need a data structure able to perform this operation. Again, we have a match, so we store again row 19, and the length of this match is increased by 1, so we store 2. Then we move again, we look for the position in the prefix array where we have row 19, but in this case we have a mismatch. So again, we need something in the mu-PBWT that help us to choose where to go. By definition, or well, is an implicit property of the PBWT. The most similar rows with respect to the one that we are considering right now are the ones that are or the tail of the run that we have ahead, or the head of the subsequent run. Because if you just take the ordering, it's quite trivial to understand that they are the best options. So we need in the PBWT something that helps us to choose between this 0, in this case, and this 0. We will see what this data structure, but suppose that we have this black box that tells us where to go. And OK, we jump to this row. We assess the prefix array. In this case, is the same value of the row, but it's a coincidence. So we store 16. We find the length of this match. We cannot just add 1. We need to explore the PBWT backward. And we continue, and we continue. Up, we have, for example, this situation where, if you look, we have len 6 in column 5, but len 4 in column 6. So it means that we have also right maximal matches, as I explained to you before, and then we can report a set maximal exact matches. We can continue up to the end of the panel, and finally report all these SMEM. As you can see, we have a SMEM here, we have a SMEM here, we have a SMEM here, and we have a SMEM here. If you look at this example, you can quickly understand that there is a problem. For example, here, I'm reporting a SMEM with the row 13, but we also have other 3 rows that share the same SMEM. So we need to find a way to discover them, but also to perform all the operations that I showed you in the example. So what we have, the mu-PBWT is composed by a mapping structure, which is an airspace data structure able to compute the mapping, is a sort of LF index, what is this? FM index that can work on the PBWT. Then we have thresholds, which store the maximum divergence array values in each run. And this can help us to say, OK, I'm above this threshold, I go up. I'm below this threshold, I go down. So this is the black box that helps us to choose where to go in case of mismatch. Then we have some prefix array and divergence array samples at the run boundary, because if you look back to the example, we are, for example, here, but I'm jumping to the end of a run, and I need to understand which prefix array value I need to use next. And the simplest way is to just store them at the end of the run. So again, we have something that is in our space. And finally, we have the feed data structure, which is, again, sublinear data structures stored in OR space that can help us to retrieve the whole set of prefix and divergence arrays. So this is just an overview of what I have already said. I want to, again, come back to an example and show you how the feed data structure works. Focus on this is the panel of the prefix arrays, and focus on 13 and 14. In column 0, they are consecutive. In column 1, they are consecutive. In column 2, they are consecutive, and so on and so forth, up to column 5, which are no more consecutive. Why? What happened? Simply, in column 4, if you think about, again, how the PBWT works, if these 2 rows underline the same bit, if you reorder them, considering that the ordering is stable, they will continue to remain consecutive. So here we have 0, 0, 1, 1, 0, 0, 0, 0, or 1, 0. What happens next? In the next ordering, the sorter will diverge these 2 values. But what happens in column 4? If these 2 values are consecutive in all the previous columns, and here they are representing a different bit, it means that they are the tail of a run and the head of the next run. So we have some knowledge about this using the prefix and divergence array samples. And we can also use this notion to retrieve the whole set, because, for example, I'm in this position. I want to know which is the next prefix array value. I can just move forward in the PBWT, reaching the first column in which the value that I'm considering is the tail of a run. And somewhere in memory, I have the notion of which value is the head of the next run. So we can just build a data structure to support these successor queries that can be performed in logarithmic time. We just store for each, let's take a M, okay, for each row where it is, for example, the tail of a run, and then we just store in a support array the value of the next prefix array value. So as you can see, if we have a maximum number of 1 equal to R, the size of these arrays at most is equal to R. So we have again a sublinear data structure that can retrieve the whole prefix and divergence arrays. Finally, we also explore the computation of MPSC using the mu-PBWT. And again, it's just a different way to scan the matching statistics array. It's not just to consider 2 consecutive values and see if the length is greater or equal to compute a SMEM, but it's something more tricky because, for example, okay, to compute the leftmost MPSC, we need to scan from right to the left and jump using the length value, while to compute the rightmost, we can just scan the matching statistics array and use the length value to drop the overlaps. So again, we have something that can take sublinear space and linear time queries. I skip this example because we are a bit late. So, of course, all these problems, so SMEM, MPSC, matching statistics, can be extended to consider at most k rows. It takes an additional data structure in the mu-PBWT, which can be computed in indexing time, and it's quite efficient to query, but we are still working on it because it's not efficient as we want. Finally, I want to show you some experiments. So just consider some public available data. In this case, for example, the panels from the 1000 Genome Project, considering just SNPs. So we have about 5,000 rows and a number of columns that span from 1 million to 6 million. We compare the mu against the original Durbin's PBWT, but also the syllable PBWT for the compression benchmark. And we compare to k-MPSC, which is a tool able to compute the minimum position substring cover, also with a coverage of k, regarding this kind of problem. We also test some non-public available datasets, such as the UK Biobank data, with the help of Dr. Rubinacci, and we tested a panel with 300,000 haplotypes and 13 million sites. Of course, the code, the source code of mu-PBWT is open source, is available on GitHub, and also all the other experiments that I have done. And as you can see in this couple of plots, on the left, we have the memory usage. This is the memory usage of the original PBWT implementation, which is up to 400 gigabytes, more or less. While if you look at the mu-PBWT querying, okay, this one is this light blue, it's about 4. So it can run on a commodity laptop. 4 gigabytes of RAMs against 400 gigabytes of RAMs, which is very, very interesting result. And if we just consider the query time, unfortunately, the original PBWT computes some index at query time, so this is not a very fair comparison, but you can accept it, in my opinion. The mu-PBWT is much, much faster than the original implementation of the PBWT. Again, this is a very interesting result. Here, we also take into account some old experiments on run length encoding PBWT, but also I want to show you what happens if we consider the including of the queries inside the reference panel. So that algorithm that Durbin didn't discuss in the paper, which is very efficient and very, very fast. But it scales. It doesn't scale on the number of queries. So you have one query or you have 100 queries, it's mostly the same. So if you have very few queries, as you can see, it becomes the slower alternative in this kind of scenario. This is just to be fair and present where the mu is good to be used and where's not. Regarding the index size on disk, the mu-PBWT is quite efficient. Of course, the BCF input files is lighter, but then we are lighter than scalable PBWT. These are the results on the UK Biobank dataset. And as you can see, the mu-PBWT in this case, because these panels are very, very, very sparse, we are even lighter than the input in BCF. Again, this is a very outstanding result. Regarding the MPSC problem, comparing to state-of-the-art tools, we are faster in indexing, but unfortunately much slower on querying. But you can easily see why. We just take, in this case for chromosome 18 from 1000 Genome Project, 2 GB of memory, against 171. So, okay, we are slower, but we can handle bigger panels. In fact, even for chromosome 2, on a machine with 256 GB of memory, the state-of-the-art tools are not able to be performed. As Simone said in the introduction, I have a slide on real-world uses of the PBWT. We have, for example, punch blocks, again, a tool developed in our lab by Dr. Jorge Villacartes, which is a tool to build a punch genome graph, starting from maximal blocks computed on a multiple sequence alignments. And these blocks are computing using the PBWT. Or we have Glimpse, which is one of the most famous tools in bioinformatics used to perform phasing and imputation on very, very big datasets and currently used to perform phasing imputation in UK Biobank data and also on Estonian biobanks, stuff like that. The core algorithm to perform the selection for the phasing is made by the PBWT. The same happens with the impute 5, which is an imputation tool, and again, it's based on the PBWT. We have, for example, pSmoother, which is an algorithm used to correct errors in large biobanks data. And again, it's based on the PBWT. Other problems can be solved: haplotype trading, IBD, detection of IBD segments, or as we tried last year, to perform genotype resolving. In fact, we tried to make a pure combinatorial approach for the phasing and the genotype resolving. Consider that in this scenario, usually tools are based on a combination of PBWT and hidden Markov models, more or less. We tried using just a pure combinatorial approach, computing MPSC that spans at most 2 columns and at least 2 rows, and try to combine this kind of anchors to detect the haplotypes that can resolve an input genotype. If these haplotypes are present, our algorithm is deterministic and fully correct. Of course, if there are regions that cannot be phased, our approach cannot say nothing. We can guess as a statistical model, but from a combinatorial point of view, we are not able to output anything. So we compared this approach against Beagle, which is state-of-the-art tool for this kind of problem. And as you can see, we scale on various mutation rate. If the mutation rate is 0, we are better. We have 0 error rate. But of course, if the mutation rate increase, we become worse than Beagle. Regarding execution time and memory, again, we scale on the mutation rate because when we try to find something outside the anchors, we become slower. But if the mutation rate is low, we are faster. And in each case, we take less memory than Beagle. So to conclude this presentation, I introduced you to the topic of the haplotype panel pattern matching using the positional Burrows-Wheeler transform. And I also present you my mu-PBWT, which is currently the state of the art in terms of run length encoding the PBWT, and we are working on a second version, which is 10 times faster and a couple of times lighter, so stay tuned. We also see some active projects that are based on the PBWT and that can be improved using our solutions, so the mu-PBWT, because, and we are working on it, because data are becoming larger and larger, and using a straightforward PBWT is no more feasible. And that's all. So thank you for your attention.
Thank you very much, Davide, for this nice talk. I hope you all enjoyed this very interesting, maybe more from computer science point of view.
I'm sorry about that. I'm a fully computer scientist and a bit more on theoretical stuff than bioinformatics stuff. So I'm sorry for this.
Well, it's okay. I think it's good to know what we actually use, how they work, and especially maybe these have pointed out to something else that can be tried. So thank you very much, and see you all in the next webinar.